Hello and welcome to Computer Tech and More. Today we're doing part of my redone series, and we're going to be taking a look at the Deep Cool FK120. Let's get right into it. A little brief explanation of what we're going to be seeing in this video. This is part of my redone series, so I did a complete reanalysis of every single fan I've tested to this point using a whole new testing methodology for noise testing. And the reason for this is my previous testing methodology I felt was a lot less consistent. I was getting plus or minus 4 decibels, so that is an 8 decibel range. And a note to remember here is that every 10 decibels is a doubling in noise volume. So that's a pretty wide range. My new testing methodology is within plus or minus 2 decibels. That is about as far as I can get with my current equipment. My microphone is just the one you're hearing me record my voice on right now. I like to get a dedicated microphone for noise testing. I'd like to upgrade my testing apparatus for case simulation testing to something a little bit more solid, so I guarantee I won't have any reverberation running through it. I would like to upgrade my anemometer to something more accurate, to hopefully something that's plus or minus 0.01 meters per second rather than 0.1 meter per second. That would greatly improve my fine-tuning in testing methodology, and make a little noise isolation chamber for around my testing apparatus. Nothing like a whole room thing, just a little one. But I can't do without help from viewers like you. All this stuff is fairly expensive, even though I'm not getting like top tier stuff, but certainly good enough. And it would help if you sign up for, well, subscribe to my channel, join me on Patreon, or want to actually just send me fans. I don't know, I'm making that part up. But I can't do this without help from viewers like you, so if you like my content, please think about subscribing, and if you can, help me out on Patreon. Other than that, I'll keep doing the videos as best as I can. The new testing methodology is plus or minus 2 decibels, right? So that involves me making sure that my room is a very, relatively speaking, consistent noise level, so the only accuracy I can get is plus or minus 2 decibels there. Make sure that I'm testing in similar noise conditions, so again, that's that variation. So if my neighbor's AC unit kicks on, I stop testing. My AC unit kicks on, I stop testing. Kid starts crying, I stop testing. And wait until the noise environment has gone to steady state. Other than that, the whole test methodology is exactly the same. I have a little piece on my channel showing off the new test methodology, and now a little bit of explanation of what we're going to see in this video. So on the right side, for all the following graphs, we're going to have the original testing methodology. On the left side, we have the new testing methodology, and they're all based around the A12X25, spinning at around 1,300 RPM, something like that, I believe. It's a 12 decibel mark. Originally, it was like 40 decibels. So that's why the noise volume on like 100% PWM signaling is going to be different, even though they're equated the same. So now I'm using a fixed pull distance away from the microphone to do the sound measurements. So as you get closer to an object, the louder it gets. So that's why the volume is going to be reduced, even though the fans are running exactly the same. The other aspect we're going to be taking a look at, or not other aspect we're going to be taking a look at, but the old test methodology is still valid, just in a very specific set of circumstances. So if you have a fan that's right up against a mesh filter, that's very similar to how I place my microphone. So in that circumstance, you're going to get extra noise going through the fan, but that's true of all fans, but this highlights that feature. Most modern cases, though, don't put mesh filters right up against the fan, but it would be equivalent to that sort of circumstance. The other circumstance would be if you have your back fan in your case as a pull configuration. So again, it's acting a lot like that mesh filter, and it's pulling air into the case so that you're basically making your case like a chimney and blowing out the top. But it'd be the set of circumstances where you have an object close up against the front of your fan. So a pull configuration in a heatsink would be another example. So it's just more limited, so that's why I've decided to move away from that testing. All right, let's get into the specifics of what we're taking. And if you are new to my channel, I encourage you to watch the second half of this video where I go into great detail with each of the tests specifically. So that's in the second half of the video, while this first half is just an overview of the original versus the new testing methodology and how they compare. So how the fans shake up in terms of their placement overall. So first up is noise normalized testing through my CPU air cooler, the U12A. Originally, the FK120 was ranked 10th, spinning out 1,600 RPM, moving 1.6 meters per second of air. It is now ranked 44th, running at only 656 RPM, moving 0.6 meters per second of air. So that is a huge drop for this fan. And it can be attested to the testing methodology where it actually performs really well with some object near in front of the fan compared to other fans, or quality control within fan sampling where I got a second sample of the fan and it ended up being a little bit noisier than the original first one. So I can't verify which it is, but either way, that is a huge difference in performance overall. At 100% PWM fan signaling through the CPU air cooler, it retains its position at 16th. Since it's not noise is not a factor here. It is a listed value, but it's not the factor driving its placement. That's why there's no change in position. Next up, cooler value proposition. Originally, it was ranked 10th. It is now ranked 42nd. So overall, a huge drop in its value proposition. At 100% PWM fan signaling, the value proposition is ranked 21. CFM testing, noise normalized, it was ranked 9th overall. It is now ranked 42nd. So again, a huge drop in its ranking. And 100%, it retains its position at 21. In terms of its value proposition, noise normalized, CFM testing, it was ranked 11th. It is now ranked 35th. At 100% PWM fan signaling, it was ranked 21 and retains that position. Moving on to the case simulation test, noise normalized, it was ranked 6th. It is now ranked 42nd. At the 11-inch mark, it was ranked 6th. It is now ranked 48th, near on dead last. So that is a huge drop in its positioning. In its value proposition, it went from 13th to 38th, and at the 11-inch mark, it went from 7th to 48th. So overall, not a great position for the FK120 to be in. Let's get into the specifics. So first up is the case simulation test. This can be looked at in a couple key different ways. The first way is, what size case do you actually plan on buying? Are you buying a small form factor case for the 6-inch mark, or are you going to be using your fans as as bottom intake fans, or I should say top intake fans, depending on the case layout, to blow air directly into your GPU? Well, then the 6-inch mark is the main factor you're going to want to be taking a look at. Small form factor being something with a front-to-back airflow, so it'd be a larger small form factor, not the ones a lot like the Fractal Design North, I believe, that suck in air from the sides and blow it out the top, or ones that blow air from the bottom through the top. You want one that's front intake and blows front-to-back airflow, because this is most important for air coolers, because you want the airspeed hitting the fan to be at as high a speed as possible so that the air cooler fan doesn't have to work extra hard to accelerate the air through it. It just has to sort of redirect the air and accelerate it into it rather than essentially pulling a vacuum, pulling the air to it. So that's why you want it to be as high as possible. For air cooler or liquid coolers, the equation is a little bit different as to what you need, but you still want good airflow going through your case. But my opinion is you would put it on the top and have it be a pull-out type scenario. So you're actually just using the radiator fans to extract the air from the case. So you still want good fans blowing air into your case, but it becomes kind of less important. I don't want to say it that way, but I guess it's true. But anyways, the 9-inch mark is representative of a compact tower. I don't have any specific models off the top of my head, but if you think something that's like a small compact tower, probably a mesh version of the lian-li like O Dynamic like mini series would fit into that category in terms of like general shape. The 11-inch mark is representative of mid-tower cases, something like the Corsair 550D, the Corsair Stormtrooper looking case, or the Fractal Meshify 2C or C, whatever the naming of it is currently, and the 14.5 inch mark is representative of a large tower, something like the Fractal design Torrent would be that 14.5 inch mark, where you want to maintain maximum airspeed across a large case. The second way to look at it is, how good is this fan at actually blowing air? So what I mean by that is the most perfect, like idealized, mathematically idealized fan would have no drop in airspeed from the front of the case to the back of the case, because the air would be a perfect, basically create a perfect cylinder behind the fan. But we don't live in that ideal world. There's going to be airspeed drops. You just don't want them to be a steep drop off and then level out. To iterate my point, so this is actually for a ceiling fan, but it describes what I'm looking at. So as the air gets further away from the fan, it tends to spread out naturally. And that's because of air resistance outside. So the air actually slows down on the outside and then it works its way to the inside. Eventually the inside air is moving at the same speed as kind of the outer parts. What you don't want is an air pattern, what they're calling a static fan in this diagram I found online. I personally don't think that any fan should be doing this in this day and age. I would want all my fans to be good concentrated airflow, because it just means it's going to slow down less and it becomes a more versatile fan. But the reason why one that spews air off to the side is less important for a radiator or even on a heatsink is because the heatsink naturally strains out the air, so the air coming out of it would be a very laminar looking flow, like very straight coming out, very little spread. If you're putting it in a pull configuration, like Linus Tech Tips recommends for front-mounted radiators, then you do want this concentrated airflow just so the air travels more smoothly through your case. This is all my opinion. I think that spreading out of airflow, it does allow for better mixing, but it's also not traveling through the case. And this is kind of my case in point with this, is you can see that at 20% PWM fan signaling, the airspeed basically drops to 0 between 11 inches and 14.5 inches. So in a bigger case, essentially without extra fans pulling the air out, so you'd need a back fan just to help pull the air out of your case. Otherwise, it's going to stagnate inside of it. Now, that's not entirely true. Eventually, it'll build up pressure inside of it and will find a way to escape, but the flow pattern will be so slow that you're not effectively cooling your case. That's basically the main case in point here. So what does all this mean? Well, I have a control fan. It's based 3 parts A12X5 to 1 part A14, blending them together to create what it isn't the perfect control fan, but it's a very good composite fan that indicates good performance versus bad performance. And what do we see from the FK120? Well, it's got bad performance, unfortunately. I like the look of the fan. How about at 100% PW fan signaling? Well, you've got the name of the fan, the RPM it's running, and its noise level. Well, it's performing nearly identical to my control fan, so it's in a good position overall. I call it in a okay to good fan category because it's close to my control fan, but it is technically, what am I reading? How about at the 100% PWM fan signal mark? Well, right here we see that my control fan is right here in this teal line, and the FK120 is outperforming my control fan by a pretty good amount. So I'd put it in a good to better category, not quite the very good mark, but certainly better. Its RPM and noise level are listed on the side, but how does it compare against other fans? This is a small sample subset of the fans I've tested thus far to give comparison points for what I consider to be good fans, medium fans, except maybe at longer distances, and then poor performing fans. So like the Wonder Snail you might think is a poor performing fan, but it actually has a fairly slow decay of airspeed, meaning that it doesn't drop much airspeed over the course of the over a longer distance. So it actually ends up being a pretty good performer and a bigger case. As for the FK120, well, it is a pretty poor performer overall. It has a very steep drop off and actually has effectively no airspeed between the 11 and 14.5 inch mark, which I did mention previously. How about at 100%? This is where the FK actually looks pretty good compared to the other fans. Now, I did include my top performing fan, the Ice Scale Extra, and it's just a 3000 RPM fan, and it just blows everybody else out of the water. So that's why it runs off the graph, because it's not that important for this scenario. But the FK120 proves itself to be upper middle of the pack, which is very good. And as a matter of fact, it actually has a slower airspeed decay than many other fans. There are very few that actually appear to do better than it, one of them being the Wonder Snail. But it's overall a good result for the FK. It just might be noisier compared to other fans. And if we're looking at its noise level in this graph, it's maximum at maximum RPMs. It's not that far off some of these other fans, but like the P12 is substantially lower than it. The A12X25 is a good 4 decibels lower than it. And again, as a note, every 10 decibels is a doubling in noise volume. So the FK is actually not terrible once you start getting air moving. So the next we have the 9-inch mark, airspeed versus decibels. And just to come back to a previous graph. So the 9-inch mark was chosen because the 11-inch mark, I had so many fans that just kind of drop off to 0 here. So it was really hard to get good, well, any data at all at some point. So the 9-inch mark was chosen where fans are still giving me enough airspeed to get good measurement data and show highlighted differences between good airflow fans and poor airflow fans while still being able to get good measurement data. Because all this changes at different distances. So this is just my chosen distance. And if you're wondering why some of these fans have joggles off to the side, that is simply where I hit a harmonic frequency within the fan that caused it to get extra noisy. And if you'll notice, my harmonic frequency, let's see, 12 decibels is around here. So that's where my noise testing was. But the fan has not gone very efficient yet at moving air. So this is the FK120. I hit a harmonic frequency, so it gets really noisy, and then it gets quiet again. So it starts lining up much better with other fans, and steeply gains airspeed without gaining that much noise. And then it gets fairly noisy again, hits another harmonic, and then comes back. So it's a very interesting result. I'd like to see Deep Cool re-engineer this fan. I have a feeling that it's got a lot to do with the blade design and potentially the motor design. It just needs to be probably thickened up, so they need a more powerful motor in it to then drive that heavier fan. But that would probably fix a lot of their harmonic problems. So I'd just like to see Deep Cool, take a closer look at this fan and try to dampen out some of the harmonics that we're seeing going on with it, because it just resonates and makes it noisy. But it's not really the worst result here. That actually belongs to the S12B, but I don't know. It's not great, but it's not terrible. So take that for what you will, I guess. Up, we have airspeed through my CPU AirCooler, which is the U12A. On the left graph, we have airspeed vertical versus RPM horizontal. On the right graph, we have airspeed vertical versus noise horizontal. The left graph is a blade efficiency graph. It is how good is this blade design at moving air at a given RPM. So right away, we can see that the FK120 is actually pretty piss poor at lower RPMs, but then it sort of catches up, timing my control fan until we start hitting greater than 1,400 RPM. Then it starts doing not a lot better, but quite a bit better than my control fan. So I'd call it a good position for it. As for noise, this is a how much airspeed does the fan push at a given noise level. So it's a noise efficiency. Here the fan is pretty bad until it hits higher RPM. So again, higher than 1,400. And then we hit another harmonic. If this harmonic wasn't there, I'd call it good enough if you want to run the fan at higher RPMs. But because of the harmonics that we're seeing in it, I just can't call it that. All right, the next one is how does it compare against every other fan? So first up, a little bit of information. This key over here is from when I did testing on my U12A cooler. I adjusted PWM. Well, I should back up. I did a whole testing methodology. It's in a video on my channel, but in the short version is I did a CPU only workload. I let it go to thermal max, 100 degrees, or not 100, 90 degrees C, where it starts clocking itself. I let it come to steady state, and then I would adjust the PWM fan signal down incrementally by 10%, or not 10%, by 10 marks. So 90, so 100, 90, 80, 70, that kind of thing. Actually, that is 10%. And would let the CPU come to steady state at each PWM fan signal. I would take the airspeed at the back of the cooler. So I got an airspeed to wattage. So I can equate the two estimated. Because every fan blows air slightly differently. So it's not 100% exact science, but it gives a good ballpark. It's gonna for the U12A and my CPU, the i7-11700K, it's gonna be accurate to within like 5 watts at a particular airspeed, which is pretty good. I mean, 5 watts does give you more clock speed, but depending on where you are on the clock to wattage curve, it's either going to be a lot or a little. So now disclaimers out of the way. So how could you use this data? Well, if you've got the same CPU as me and the same cooler as me, you can just use it verbatim, like pretty much exact. But if you don't have the same CPU as me, the wattages may not line up perfectly. If you don't have the same cooler as me, the wattages don't line perfectly. So how can you use this data? Well, if you have a non-K Intel CPU, so it's not unlocked, if you start off at, let's say, the FK120 noise normalized and you upgrade to the ToughFan 12 Turbo, well, now your CPU is probably going to run cooler for the same wattage that it draws. If you're using an unlocked CPU and you've got a different cooler than me, it allows you to go, hey, I can get additional wattage by going from this fan to going with this fan. How much extra wattage? I can't say for certain because every cooler is different, every CPU is different, even within the same product lineup. The amount of wattages per clock speed are slightly different between every processor. So I can't say that for certain. And the other way to use it is, hey, I've got this CPU or this fan, and I upgrade to this fan. I think that your normalized level is too noisy for me. Well, you can back off that PWM fan signal to match the airspeed of another fan. And now your computer is going to run quieter for the same thermal load. Whew, all of that said, how does the FK120 rank? Well, it's pretty far down at the bottom of the graph. So no need to talk about that further. How about at 100% PWM fan signaling? Again, wattages per airspeed. Here, the FK120 struts its stuff, being in the upper half of the graphs. And beyond that, its noise level is actually pretty reasonable compared to other fans around it. I wouldn't put it in the best category for fan noise, but it's certainly in a better category. And it is outperforming in my testing other competitive fans, such as the A12X25. It is pushing more air. And I should note that I did note before, anemometer is accurate within plus or minus 0.1 meters per second. However, I do repeat testing, averaging results. So the value, the ranking is what the ranking should be. Just note that the fans may have effectively the same airspeed because of the accuracy of my current equipment. How about airspeed through the cooler versus decibels? Well, the FK120 shows it's not very good overall. It's those harmonics. It could do so much better in whatever is going on here. They need to figure out this part where it's getting this nice steep climb and figure out how the airflow is traveling over the fan at that range and just reshape the fan so that it continues along that path. Next set of graphs is RPM is CFM testing. So I'm not a huge fan of CFM testing overall unless it's for specific use cases. A lot of YouTube channels and channels in general use CFM testing to talk about this fan is good for cooling, for case cooling. That isn't accurate. It might be, but that's why there's the case simulation test. In essence, the CFM test is you've got a tube that is the size of the fan, so there's no room for it to spread out. To calculate CFM, so CFM is cubic feet per minute. You know the diameter of your tube, so divide that by 2, R, square it, so R squared. So let's just say that was in feet, so feet squared. And you know pi, so 3.14, so it's a circular tube. So pi R squared. Anyways, you know the airspeed, so let's have that be in feet per minute. So feet squared for the surface area times feet per minute. So feet squared times feet is feet cubed per minute, cubic feet per minute. Hooray! We did math. But when you're blowing air down a tube, so let's say the fan, you have a diffuser on the fan and has a tendency to make the air spread out. And you have another exact same fan and you have one that helps align the air so it's now traveling in a straight line. And then you put them in, have it smacked up against the tube. Well, the diffuser might be trying to spread out the air, but the air has nowhere to spread out to because it's still traveling down the tube. So the air speed is going to look a lot closer to the one that has a concentrated airflow than it would in my case airflow test, thus hiding the fact that if a fan has a tendency to spread out air, is still going to look relatively good compared to one that has a focused airflow, and so you're not going to see the real data. It's not giving you the best information. So that's why I think the case simulation test is actually the way to go for getting information as to which fan is best for your case airflow. Now, CFM testing is good for a couple different things. If you want to make your own at-home wind tunnel, very valid. If you want to calculate PQ curves, so you'd have a pressure sensor, you'd have a plate with a restrictor in it, and then you have a pressure sensor on the other side. A lot like what Noctua does, like PQ curves to measure how good this fan is at a different pressure type scenarios. That is very valid. The only exception is in raw airflow. Now, you can relate them all to each other within that test, but it doesn't tell you how good the fan is actually like focusing the air. But it will tell you how good the fan is at blowing air in a number of scenarios. So it's very valid for that set of circumstances. And it's also valid for if you want to test your heatsink or radiator, max total airflow traveling through it. Very similar to my heatsink test, where I'm just measuring airspeed, but it would be very easy to turn that into CFM because I know the surface area of my heatsink. I just chose not to convert it to CFM. I left it as raw meters per second, or meters cubed per second. That would be the equivalent of CFM in metric. So you can just choose how you want to use it. And the last way that you could use CFM calculating is for total airflow through your case. So you've got your fan at the front, and let's use the Fractal Design Torrent as an example. So it's got no fans on the top, and we've got the fans on the bottom blowing air in. So that means there's only one area for the air to exit, the very back of the case. I could set my anemometer to different areas on the back of the case and average the airspeed exiting the case, getting a total CFM traveling through the case. So that is a way to calculate CFM that is valid for case airflow. But just poking it up to a tube and going, this is the CFM value, this fan is good at blowing at case airflow, that is fundamentally incorrect, and any channel that is saying that, their testing is flawed, and you shouldn't trust them. They don't understand the science. I am an actual aerospace engineer with a specialization in fluid dynamics. Just saying. Okay, so we're going to move quickly through these tests. They're very similar overall to the heatsink test. So airspeed in CFM in the vertical axis, and RPM or decibels in the horizontal, depending on the graph. And how does it compare to my control? Well, they line up near on perfectly. No surprise. How about noise versus CFM? Well, the FK120 once again underperforms. At 100 or at noise normalized compared to other fans, well, it is towards the bottom of the graph, but it isn't utterly terrible compared to the worst ones. But it is at the bottom of the graph, so thus it would not be recommended for noise normalized results. At 100% PWM fan signaling, it appears to be basically smack dab in the middle, so take that for what you will. And here is CFM versus noise, again towards the bottom of the graphs for what I consider it's a good like case study of fans that it should be competing with. Here's the basic spec information for the FK120 by Deepcool. It is a pretty much bog standard 120 millimeter fan standard. All right, we are on to the value proposition. The FK120 is a $20 fan. So for calculating performance per dollar, it's literally airspeed or CFM divided by dollars, and it's just as simple a calculation as that. So who is these graphs specifically for? Well, if you're on an ultra tight budget where you're trying to squeeze every penny out of your build to get the best you can for the absolute minimum amount of money, you would want to pay special attention to these graphs, because this is where you're going to get the best fan for the least amount of money. It's not going to be the best fan, but it gives you that best performance per dollar ratio. If you have a little bit of extra money and some flexibility with where you're spending it, so you want to get a little bit better fans for noise performance, you want better airflow performance, you want a particular style, or you want RGB, then you'd weigh in the performance data that I'm presenting here with the performance data that we saw before to determine which area is the most important to you to select which fan you want. And then, of course, if you want RGB, then you'd be selecting its RGB and which style RGB. And by the way, I will have upcoming videos on my best RGB fan tested so far, best cheap fan, so under $18 fan, and best overall fan. Those are all coming up on my channel after I've finished basically this overall. So what are we seeing overall? Right now, for all the graphs, the left side is going to be noise normalized, right side is going to be 100%. The FK120 is towards the bottom of the graphs, so no surprise. How about at 100% PWM fan signaling? Well, it's in the upper middle, but it's a far cry from the top best fans. How about at the 11-inch mark, noise normalized? Well, it has an airspeed of 0, so it's utter trash. At 100% PWM fan signaling, it is in the upper part of the graph. However, the other fans that are much cheaper in value just completely blow it out of the water, so thus making it not the best fan for case airflow application. How about in a cooler? Well, noise normalized, it is still towards the bottom of the graphs. However, at 100% PWM fan signaling, it is upper middle. So also not a great position for it to be in right there. How about in CFM testing? Basically in the middle for noise normalized results. Actually kind of below middle now that I'm looking at it more closely. At 100%, well, it is technically in the upper middle, but it's just such a far cry from the best fans. So where does that leave me with the FK120? Well, I think the FK looks pretty cool. There's no fan on the market right now that looks like it with the wide tips, narrow body. But its value proposition isn't that great. Its noise normalized performance isn't that great. Now, it could be that the samples I got were part of a batch that were just inconsistent and noisy. I know I've heard about it from their cooler review that some of their fans have been on the noisy side. So it could be that I just got a couple lemons, but that leads into another problem. How can you guarantee that you're not going to get a lemon when you buy the fan? and then have to deal with returning it and getting a new one, and yada yada yada, that sort of thing. So there is an inherent risk with purchasing this fan, going through that. So I can't make that decision for you. I think it looks good. Its overall performance isn't bad, but it's just a little bit under the best performing fans. So really, you're only going to buy it if it comes with your case, your cooler or whatever, or you just really like the style. That would be why you have this fan. I guess for me, I wouldn't go out and buy it just on its own. But that's a decision for you to make. All right, let's go to my wrap it up section. All right, and at the end of every video, I like to show off the raw data. This is the raw data for the FK120. Over here, you have how it sounded in a pull configuration. So in a pull, I found a high-pitched, but fairly quiet. I found that had severe harmonics, but onto the what I actually want with this data. So you are welcome to use this data for your own purposes. If you're going to put it into your own Excel sheet for you to do your own calculations and compare fans however you want, so resetting this decibel reading, you're more than welcome to do so. But if you're going to use it in any journal, publication, video, anything like that, I do ask that you reference me and my channel. I own this data. I created it. I am the originator. So please reference me. It takes me around an hour and a half to 2 hours per fan to do this level of testing that you saw in the video. Plus, it takes more time to update graphs and limit the data for presenting in my PowerPoint presentation, and then, of course, to record the video. So I do thank you for that reference. If you have constructive criticism on how I can improve my videos, please leave it in the comment section down below. And if there are any fans you wish to see in the future, please leave them in the comment section down below. I do spend time and read it and answer questions as best as I can. Please subscribe for more content, and I would really appreciate it for you all to join me on Patreon. I'm still figuring out putting videos on it, links on it. I don't really have any behind the scenes because it's just me sitting around collecting data. So I'm not sure that would be really interesting. But I'm open to do that if you want to see what my office looks like, I guess. But anyways, yeah, thank you for watching my video. I hope you have a great day, and I hope to see you next time here on Computer Tech and More.